Let's talk about a couple properties that go with bases and vector spaces, namely the idea of dimension and the idea of rank. These are two pretty similar ideas, so I'm combining these two homework sections into one. So when you turn in your homework, you can just do one document that has both 4.5 and 4.6 with one report at the top and all that. But let's talk about this idea of dimension. So let's motivate this with an example. I'll take you back to the idea of a basis. And we have said before that a basis is not unique. There can be a lot of different bases for R2, for instance, for that vector space known as R2. So my question for you here is, I've got 1, 2, 3, 4, 5, 6 examples of possible bases for R2. And I'd like you to pause the video for a second and just decide which one of these are bases and which ones are not. So pause and then come back. Okay, so keep in mind a basis has to span R2, so you have to be able to get everywhere in R2, and it also has to not have any extra vectors that aren't needed for the spanning. So starting with B, you have two linearly independent vectors in R2, which is exactly what you need for a basis. So you know that the span of 2, 1, and 1, 0 you can get anywhere in R2 space. And there's no extra vectors there, so that's a basis. That one works. C, it's also, these two are linearly independent of each other, and they're two R2 vectors, so that's good. D, you can probably get everywhere. You can get everywhere in R2, but there's 3 vectors. That's too many. You don't need that many. So this one, like 5, 2, you can get to by using 4, negative 1, and 2, 3. I don't know exactly how. Actually, if this had been 6, 2, then it would just be 1 of the first one, 1 of the second one. But even as 5, 2, there's a way. It probably involves some fractions, but yeah, this one's not a basis because it has too many vectors. G right below it is also not going to be a basis. Too few vectors, right? You can't get everywhere. You can only travel one direction. You can go in the 1, 1 direction, which is kind of a 45-degree angle. You can travel a 45-degree line that goes through the origin using G by various multiples of G, but that's it. You can't get to all of two-dimensional space. E is the standard basis. You can definitely get everywhere in two-dimensional space with that, and there's no duplication. These are linearly independent vectors. F is 2 vectors in R2, but notice they're multiples of each other. So F graphically looks somewhat like G in that you can move in the 1, 2 direction, and you can move in the 2, 4 direction, which is the same direction. So you can travel along that line that's 1 over and 2 up, or 2 over and 4 up. You can travel in that direction, but not all of R2 can be reached with those. So we had 1, 2, 3 that were bases, and two more that were not. Sorry, 3 more that were not, for various reasons. These are not independent. So notice that all 3 of my ones that were actually bases had the same number of vectors in them. They each had 2 vectors. Kind of makes sense for R2. I know we know this, but it's worth pointing out here because that's exactly what we mean when we talk about dimension. So I don't know if this is worth pointing out because, like I said, this is pretty basic information for us at this point, but this is a theorem in this section that just says if you've got a basis, then any set containing more than n must be linearly dependent. So you've already got the basis, like D is a good example. You already had the basis right there. And then with that extra vector, that one had to be linearly dependent. And we know how to find linearly dependent vectors, right? You row reduce. Non-pivot columns are the dependent ones. Pivot columns are linearly independent. So we could do that to D, make it a 2 by 3 matrix and row reduce, and you'd see pivot columns in column 1 and column 2. That would tell you those are the linearly independent ones, and the third one's dependent. But anyway, let's get to the real definition here. And this, of course, is the book's complicated way of saying this, but I said if you've got V and it's spanned by a finite set, first of all, then they call it finite dimensional. So in our case, these are spanned by sets with 2 vectors in them. So they'll be 2-dimensional. But in general, they want to make a distinction between finite dimensional and things that are infinite dimensional. But the dimension, which is abbreviated this way, just dim of V, dimension of a vector space, is the number of vectors in the basis. There it is. That's what we were waiting for. It's just the definition. How many vectors are in the basis? That's the dimension. There is such a thing as the vector space that's just the 0 vector. And even though it sort of technically has one vector in it, by definition, the 0 vector space is defined to have a dimension of 0. They also do point out, since we're on vocab, if V is not spanned by a finite set, then it requires an infinite number of spanning elements. Then it's infinite dimensional. One good example of an infinite dimensional vector space is P, which is the set of all polynomials. All right, again, you can have P sub 2, and a basis for that would be, so P sub 2 could be the span of 1 and T squared. That'd be one way to generate all polynomials of degree 2 or less. And there's others, of course, other bases that would work, but this is one. So that's P2, and it's spanned by 3. But just P in general, all polynomials would require an infinite number of spanning elements here. It'd be 1 and T squared and T cubed and T to the 4th and T to the 5th and T to the 6th. And this is where a mathematician goes dot, dot, dot. Take an infinite number of elements. So that would be an infinite dimensional space. Okay, but I just wanted to point out one of the reasons that we care about dimension is it tells us something about where we can go and what we can get to. So consider R3, and let's look at some subspaces of R3. So let's say that we have a subspace that is just defined as the numbers here don't really matter, but just as a span of 1 vector. So it says you can do any multiple of 1, 2, 3. So obviously the dimension there is 1. Graphically, what that means is you can move in exactly one direction, and you can go however 1, 2, 3 goes, kind of out this way from the origin. You can go anywhere in this direction. So the subspace that we're talking about is a line. Now let's imagine a subspace that has dimension 2. So like the span of 1, 2, 3 and -1, 0, 5. Now you've got 2 directions that you can move in, and your span can be the combination of any of those 2 vectors. So that means not only can you move sort of this way, but you can also move off this way. It's so hard to draw like planes on top of axes, but yeah, that's terrible. But what you get is a plane. You get a flat sheet in three-dimensional space. So you have dimension is 2, and graphically you're talking about a plane, which is something we typically think of, a flat sheet as a two-dimensional object, where we think of a line as a one-dimensional object. And if we do have something that is dimension 3, that would be the span of 3 vectors, or basis of 3 vectors. I'll just use the standard ones for lack of creativity. Could be any 3 linearly independent ones. Now you can go in 3 different directions. You can get everywhere in 3 space. So I'm not trying to draw a plane anymore. I'm trying to shade in all of 3 space here. And I don't know if that's exactly a shape, but you could call it something like, it's not a line, it's not a plane, it's an infinite cube or something. Sort of think of a cube because you're moving in 3 directions, but it fills all of 3-dimensional space, which is what we like to call 3-dimensional. And finally, if we do take a look at a dimension 0 subspace of R3, that would just be the span of just the 0 vector. And all multiples of the 0 vector, whatever you multiply it by, you're just a point. You sit right on the origin. That's all you get out of this. And a point, a line is 1-dimensional, a plane's 2-dimensional, an infinite cube is 3-dimensional. A point is 0-dimensional. And that's a point. So this sort of formal definition of how many vectors are in the basis of the vector space matches our general geographic intuition of saying, hey, if you can move in one direction, it's a 1-dimensional vector space, and that graphically ends up looking like a line. And if you can move in 2 directions, you make a plane, and that's 2-dimensional vector space, and so on. All right, in the next video, we'll unpack more of the computations.